What? Oh, sure.
So thanks everyone for coming in to participate, and indeed it is participation which makes a meeting successful. So here at UCL, Jonathan and I have been recently concentrating on kind of low energy tests of quantum gravity or quantum nature of gravity, and various allied topics in the interface of quantum and gravity, but not necessarily like Planck scale high energy physics, but what we can do, what other insights we can get in low energy. And the plan is eventually to make a center on this activity over here. And this, we don't yet have any funding for that, but this is kind of a starting point from for come together. We had a few visitors coinciding visit at this time, so we decided to organize this meeting for everyone's visit, and then we were also lucky to get some other visitors by chance we didn't know about. So that's great. Yeah. So let's start with the first session. Yeah, we get to know that.
I'm one of those visitors by chance. So thank you, Sugatu, for letting me know. And I'm going to chair this session. So our first talk is by Gautam Satishchandran, sorry, because it's hard for me to pronounce, from Princeton University, and he's going to talk about black holes and decoherence.
All right. Can everyone hear me? I hope this microphone works. Okay. Right. So thanks for the invitation, and it's nice to see some people I recognize and some people I don't. So I always like coming back to UCL. Every time I come to London, I make sure to visit Sugatu and Jonathan and say hi and figure out what they're up to. Okay, so what I'll be talking about today, well, I've listed a lot of papers here. So first of all, don't be concerned. I'm not going to talk about almost all of these papers. I'm gonna largely talk, this is basically just to list the series of works, which was really kicked off by this first paper in 2021, or pair of papers in 2021, which then subsequently spawned a whole series of investigations by myself and my collaborators. This is Dane Danielson, who will be a postdoc at Harvard next year, and or I guess this fall, and Bob Wall. And this spawned, well, a number of investigations by myself and my collaborators, but also by a number of people. I've just highlighted 4 such papers. There are several more I didn't. And I'm happy to talk about any other kinds of investigations too. And what I'll really be talking about are just the ones highlighted in blue. Okay. And in particular, I'll mostly be just talking about this first paper that we discussed, which shares the name of this title. And of course, the point of the talk is to explain the title. How do I advance slides? Good. Okay, so I'm the first speaker of this symposium, and I'll be talking about quantum gravity. So it's useful, I think, at this stage to first orient the discussion, explain what I mean, but when I'll be talking about quantum gravity and so forth. So, well, quantum gravity has been investigated by a number of authors over the century. I just came from the GR meeting in Glasgow, and at that meeting there were probably as many theories of quantum gravity as there are participants of the meeting. So there, really the key issue of quantum gravity, or one of the key issues, is that we don't as yet have a fundamental theory of quantum gravity, as opposed to many of the other theories that we work with. That's what makes it exciting, but what makes it very difficult. Also, well, at least in the time of the 1960s, when this quote was taken, there weren't many experiments to adjudicate the different theories of quantum gravity that people had in mind. So this was at this Chapel Hill conference. This is what is now known as GR1, I guess. So we've come a long way since then. And Well, many people were at this conference and in attendance. Feynman was in particular at this attendance. I think he told his wife afterwards, make sure to remind me to never go to a meeting with relativists after this, because he got pretty annoyed. What he was mostly annoyed about was the fact that one wasn't really thinking in terms of observables and experiments. And well, the situation is much better nowadays in the sense that we have some experiments to be able to probe some features of quantum gravity. However, what Feynman was advocating, and that's what I'll be kind of pushing forward in this talk, was, you know, even if you don't have experiments, it's useful to pretend like you do. Okay, and just while you pretend like you do have those experiments, ask what the outcomes of those experiments are, and using those outcomes, figure out you know, some fundamental properties of the theory. In particular, what he was really advocating was to probe the fundamental properties of quantum gravity. It's really useful to consider situations where both quantum theory and gravity play an essential role. In such a situation, one can use the well-understood rules of the quantum theory to then conclude things about the fundamental theory. So that's what, well, that's, you know, I've investigated this, you know, at the level of the superpositions. This is the mass in a quantum superposition that's going to actually play a role in later parts of my talk. Those of you who know Sugato's work and others will recognize that kind of setup. But the basic point of this talk is we'll show, just following the same idea that Feynman was pointing out in the late 50s, is that we'll show that black holes, or really any horizon, will impose fundamental bounds on the coherence of any quantum superposition, in particular setups like this, where you have superpositions of gravitational fields. Jonathan, you have a question? Yeah.
Keep it to this side.
Sure. Yeah. Sorry. Where is the
metal bar there that you're responding to?
So I'm quite contained. Okay. Let me try that. Yeah. Yeah. Okay. Well, I tend to walk around, so I hope I don't random walk out of the room. Okay. So. Okay, cool. So that's the basic setup. This slide has almost no content, but hopefully pushes you in the direction that we'll be thinking about in this talk. So, well, first, you know, well, why should this even be the case? Yeah, go ahead.
So it's a very naive question.
Yeah.
So when you're talking about quantum gravity and measuring it, right, then automatically it seems to me that you're thinking about G mu nu, T mu nu. You've already taken it.
Yeah. So all of those kinds of questions in terms of what I'll be doing and the calculations will be clear. Yeah, everything will be perturbative quantum gravity off of a background space-time. Is that clear?
Yeah.
All right. Yeah. So good. So why should that even be the case? And you can, well, how do I advance? So I'll explain basically the conclusion at various levels of rigor. Okay. And here on this slide, you'll basically, well, I'll be explaining this conclusion at what in America I would call the PBS special level. Does anyone know what PBS is? Okay. Yeah, exactly. So here, I guess it would be the BBC special level. It doesn't require any equations, and you just can see it from kind of basic principles of both quantum mechanics and causality. Okay. So, well, in order to understand this, consider an experimentalist, Alice. So there are experimentalists, I think, in this room. Okay, so, or maybe there are, or at least people who think about experiments. So I'm not one of them. So Alice is one of them. She manipulates a quantum superposition, which she wants to keep coherent. Okay, so that's familiar to those of you who make quantum superpositions. Alice is one such person. This is her in her lab with her, her lab mate, and they're working on their quantum computer. That quantum computer has qubits in it that she wants to maintain or keep coherent. Okay. That she wants to keep coherent, and as a result, well, why would she be worried about any loss of coherence? Well, as anyone who's ever tried to make a quantum superposition, you already know the answer to that. Everything in her lab could possibly decohere her quantum superposition. For those of you, well, in the GR meeting, I had explained what decoherence was. Probably less so here, but I'll still explain it in words. Anyway, well, this occurs because any degrees of freedom of her environment may respond differently depending on which branch of the superposition her qubit is in. So for example, the gas molecules in her room will collide with her quantum superposition. If it collides with her quantum superposition differently on one branch than the other, then the gas molecules in the room will be entangled with her superposition, and thereby she won't be able to perform any sensitive interference experiments that she'd want to do to run her quantum computer. She's going to lose all their funding pretty quickly if she can't cool down her room at least. But that's not enough. Obviously, there's wires in her lab, stray electromagnetic fields. Those stray electromagnetic fields may cause some differing motions of her particles that she's trying to keep coherent. She's got to electromagnetically shield her apparatus. Let's give Alice all the funding in the world. Let's make sure that she can reduce all sources of decoherence in her lab as she can. This is Sugato's dream. Yeah, we would like that. Everyone would like that. So let's do that. Let's fund Alice as much as we can, at least to the end of the slide, and we'll see what she can do. Okay. So, okay. So why? Well, in any good Gedanken experiment, there's an Alice and a Bob, right? And in this case, Bob is a bit adversarial. He is jealous of Alice and her ability to maintain coherence. Okay, she has so much funding, and he has no funding. Okay, but it's easy to destroy coherence. It's not easy to make it. So what Bob realizes that he knows that despite Alice's best efforts, she cannot control the long-range gravitational field of her superposition. So if her superposition gravitates differently on one branch or the other, those long-range gravitational fields, she's not going to be able to shield those. That's going to go off and go to the exterior of her lab. And what Bob realizes is that in principle, any quantum superposition of gravitational fields can be measured. What I mean is release an apparatus and entangle your apparatus with that via the gravitational superposition. And that'll give rise to some degree of decoherence. So people at GR22 got a kick out of this. So this is Bob. Bob is jealous of Alice and her ability to maintain coherence and decides, well, what I'm going to do is just go outside of Alice's lab. She's controlled everything in her lab. There's no source of decoherence in her lab, but there's these long-range gravitational fields that go out of Alice's lab. And Bob, what he's going to do is just measure those gravitational fields. That's a really good idea, except for the fact Bob realizes something, but Alice is wary of Bob and could just open the window and look and see that Bob is there, right? So Bob realizes something. He doesn't want to get caught. Someone has a question. Yeah.
You're speaking about the very soft gravitons here.
No. This is the long-range Newtonian field of the qubit that she's now made in a superposed state with two different gravitational fields. Good. We'll get to that later. Good. So Bob has a really good idea. I hope you think it's a good idea. I mean, it's a very hard experiment, as many of you undoubtedly know. But Bob, again, is a pretty good experimentalist and can, in principle, do this experiment and destroy Alice's coherence. Okay, but Bob doesn't want to get caught. So what Bob realizes is, well, here's one way to not get caught. The long-range gravitational field, so Bob didn't really like this too much when I put him in a box, but the long-range gravitational field of the qubit has no problem, well, if the black hole wasn't there, has no problem going outside of Alice's lab. If the black hole is there, it still has no problem penetrating into the interior of a black hole. But And so you'll have inside the black hole, again, a superposition of gravitational fields, whether or not, the qubit had gravitated differently on one branch than the other. Could I maybe finish the Gautam experiment? So, okay, so Bob is inside there and has no problem, again, doing this experiment in the interior of the black hole. But then this Bob knows something about general relativity, right? And he knows that he realizes something, right? As he's about to collapse the star and form a black hole and jump inside it, he realizes that he doesn't even need to jump inside it. Because by causality, Alice can't know that Bob is inside the black hole. Any measurement that Bob does in the interior, which would entangle and thereby decohere Alice's superposition, this decoherence must occur even in the absence of Bob itself. Okay? Because there could be a Bob making a measurement inside the black hole and thereby decohering Alice's superposition, Alice's state must be decohered itself by that possibility. Okay? By the presence of the black hole itself. Maybe I'll just put a finer point on it and then I'll take your question. Okay, so let me repeat it again. I hope the pictures help. The fact that Bob could make a measurement to decohere her superposition implies that it must be decohered in the absence of Bob. That just follows from causality and the basic principles of quantum mechanics. Thus, black holes must decohere quantum superpositions, and importantly, and we'll see this later, as if they're measuring its long-range gravitational field, as if there are degrees of freedom inside being able to measure the long-range gravitational field. Okay, let me take your question now.
Yeah, I'm having trouble imagining the Newtonian gravitational interaction on the interior, interacting with the interior of the black hole, because the stuff inside the black hole can't, interact with the.
No, it's a one-way street, but in the other direction.
Right, but it's a one-way street.
No, but so the Newtonian field has no problem going in the black hole,
Right.
but your interaction with it
Right,
will,
that's my problem.
your interaction will causally, yeah, so Bob inside the black hole will become entangled with Alice's particle. They'll become entangled because Alice's particle, let's say, well, I'll be more explicit in a second, makes a superposition of gravitational fields. And the gravitational fields thereby encode which, let's say, path the particle went on.
I'm fine with that. I
Yeah.
just have trouble with the Newtonian interaction, which is equal in both directions and can't be equal implicitly say.
Well,
with something inside the black hole Alice cannot detect the thing what's happening inside.
well, that's kind of the whole point of the thing, but the point is that the only way, you only need it to go in one direction. So in order for the entanglement to occur. Now the question is, why is any amount of entanglement generated consistent with causality, which is the statement that Alice can't know that Bob is inside? That's the whole point of the rest of the talk. Yeah.
The put-to-shoot translation happens in quantum mechanics. If you have an are you assuming some kind of structure inside the black hole?
No, it's vacuum GR.
So this
So
logic.
that Bob is the only structure.
Okay.
Well, but then anything that Alice does outside the black hole, once the black hole,
Cannot have any
from the point of view of Alice, her signals never reach the.
No, the gravitational field does. The long-range gravitational field of Alice's particle does go into the interior.
Any change.
No, we're not doing, yeah, I agree.
Anything.
Yeah.
For outside observer is frozen out.
No, the gravitational field goes off and enters. We'll see it explicitly. If I hold a Newtonian field outside a black hole, a massive body, the long-range gravitational field goes off and into the interior. You can measure it on the inside.
Yes, it's goes so long as you probably. So long as you can hold your observer indefinitely.
No, in finite time. Well, I'll show you in finite time. It's in finite time. You'll see that there's a non-zero Newtonian. It's a solution to the field equation of Alice and Bob. Well, yeah, maybe. No, it does. It's totally covariant. You have a mass. Okay. And I move it from one location to the other. You can ask, when inside does the gravitational field change? It changes, there's a retardation effect. but the gravitational field inside the black hole will change. And therefore, when Alice makes a superposition of gravitational fields, we'll see it explicitly. Bob inside, there's a retardation effect, of course. I mean, there in finite Bob's time and finite Alice's time, he sees a change in the gravitational field if Alice takes a massive body and moves it from one location to the other.
Okay, that would mean that massless particles will cross the event horizon of the black hole in finite time of X.
Yeah, that's right. Well, I mean, it depends on what you mean. Any any disturbances will be seen by and influence a Bob's experiment in the interior. There's no difference between the two. Any yeah.
That's an interesting point. So let's
Yeah.
remember it and
Yeah. No. It's a really good point, and it's true.
no.
Which is the yeah. No, I mean, if I just stick on this slide, that's fine. I'm happy to, but I'll explain it quantitatively too, if you want.
Yeah, please do.
What? Okay. Okay, so basically what I've explained, this is how we concluded that this effect, the following effect, oh, sorry. This is how we concluded that the following effect that I'll describe in the rest of the talk exists. Okay, but however, this argument didn't appear in our first paper because, well, for the same reasons as we were just discussing, it seemed a little loosey-goosey. We wanted a real concrete experiment in the exterior. So the rest of the talk does not rely on anything that I'm saying here. The rest of the talk does not have a Bob at all. We'll just have an Alice in the exterior of a black hole, and we'll see, indeed, this fact is true. Okay. However, I hope this presentation was useful to understand how we concluded that the effect exists. Okay, so to make this a concrete experimental question, we now have to have a concrete experimental setup. Okay, so what we're going to have is Alice is going to have a very specific setup. The specificity of the setup is not important for the generality of the conclusions. It's specific because then we can do a concrete calculation. Okay, so what we're going to have is Alice has a massive particle, let's say, with spin. Why does she have spin? Well, she's going to make her quantum superposition by passing it through a Stern-Gerlach apparatus. So maybe it's worthwhile to just show you a diagram. So Alice's particle with spin is right here, all the way at the bottom of the diagram. She passes it through, let's say it has initial spin in the x direction. She passes it through a Stern-Gerlach apparatus. That's going to make a 50-50 spatial superposition of having gone to the left with spin down in the z direction, or having gone to the right with spin, let's say, up in the z direction. If the Stern-Gerlach is oriented in that direction. And the size of the separation, of course, is determined by the strength of the magnetic field in the Stern-Gerlach apparatus. So she's going to make this 50-50 spatial superposition, and then she is going to hold this superposition for a time t in her lab. And she holds it stationary, so now she's made this spatial superposition, and after a time t, in order to make an experimental question, she's going to check for coherence. How does she do it? She passes it through a reversing Stern-Gerlach. She just flips her Stern-Gerlach apparatus upside down, passes the beams of her particle back together, and then checks for coherence. She can do that by checking the x spin of her particle. Initially, it had definite spin in the x direction. If she's a perfect experimentalist, and as we'll see later, not outside a black hole, then she'll ensure that she has definite spin in the x direction. If she ever sees spin down in the x direction, she knows she's decohered, but she doesn't know how much. She's got to get more funding to redo the experiment. Okay, everyone understand the setup? Okay, for simplicity, actually, for most of this talk, I'll deal with the electromagnetic version of the story, where Alice's particle, we neglect the mass and we really care about the fact that it's charged. Okay, that's the key point. There's a gravitational version which is almost identical, but it's conceptually simpler to first think about photons, and then gravitons are treated in almost an identical manner. Okay. Okay, so let's now just first consider the case of flat space-time. So forget Bob, forget black holes. Alice is just doing this experiment in flat space-time. And again, she's a perfect experimentalist. So there's nothing that could possibly decohere her, except for the fact that she's coupled to one environment, which is the electromagnetic field. And thereby she will decohere due to the degrees of freedom of the electromagnetic field. In particular, if she emits any radiation along path 1 of her superposition or path 2 of her superposition. And if this radiation states, if that environment responds differently, if these radiation states are sufficiently orthogonal along path 1 and path 2 by the superposition, then she will be decohered. If these are orthogonal, then the decoherence here is 1. If these are not orthogonal, then she's not decohered. Okay. And it's useful, a formula that will appear later in the talk is you can rewrite this in terms of the expected number of so-called entangling photons. So what this number of photons is you take the number of photons in the difference of the radiation states of the two particles. Along path 1 and path 2. So if there's a non-zero number or a order 1 number of this entangling photons, the number of photons in the difference of the radiation states along path 1 and path 2, then Alice is essentially totally decohered. Okay. So this is a diagram in flat space-time, and you don't need to know what most of these symbols mean, meaning this one or this one or this one. But the basic point is that she's doing this experiment. She could decohere by some radiation. The state of her particle is given here, where there could be some radiation along path 1 or path 2. Okay, but it should be intuitively obvious that the only time she's going to radiate in this process is when she opens the superposition and closes it. Those are the times when she's accelerating the branches of her wave function. And if she makes that time sufficiently long, you can calculate specifically how long, that radiation will be totally negligible. Though both radiation states will be essentially in the vacuum. This should be intuitively obvious to most of you, which is that if she just does her separation slowly enough and recombination slowly enough, she should not be decohered by any radiation. Okay. So the whole point or rest of the talk is that this conclusion, by the way, that I just concluded in flat space-time, which is that if I separate and recombine a particle, no matter how slowly in flat space-time, I will not be decohered. Based on the previous slide, what must be the case is that in the case of a black hole, a quantum superposition is going to be forced to emit entangling radiation into a black hole, no matter how adiabatically Alice performs the experiment, if the conclusions of the previous slide were true. Okay. So, and what we're going to see is that indeed that is the case, resulting in a constant rate of decoherence. Okay, so this is the setup. This is the star. I think it was mentioned earlier. Black holes are formed by collapse of stars. So this is the star that way in the past of Alice's super. This is a conformal diagram, so all the scales are off. So this happened millions of years ago. Alice got her funding a million years later. She started making her superposition. Maybe I'll just explain the diagram. So she's making her superposition. Now she's got to be in a rocket ship. I mean, she doesn't have to be. It's just going to make her life way worse, because if she's falling into the black hole, she'll be radiating like mad. So it's important that she's in a rocket ship and she puts her superpositions in traps in order to make sure that they go on optimal trajectories. If they follow the killing field in the exterior of the black hole, then they'll ensure, they are separated adiabatically with respect to the killing field, then that's going to ensure exactly the same conclusions as before. She's not going to radiate anything to infinity if she separates and recombines arbitrarily slowly along the killing field in the exterior. However, what must be the case is that no matter how optimally she does things in the exterior, she must decohere due to some radiation into the interior of the black hole, no matter what. And indeed, what we're going to see is that this is not zero. You had a question.
Sorry, I wasn't all this question, but I think it's better if I tell you now. And
Okay.
it's really silly and it's necessary. So can you pinpoint what is the relevance of the event horizon? Because
Well, the-
Bob like measure anywhere in space time. So
yeah. It's, well, Bob can measure anywhere in space-time. This picture doesn't have Bob in it.
yeah.
So in order to, so what we concluded is that event horizons must play a similar role to a Bob or a glass of water or the other degrees of freedom analysis lab.
Is it something like that if there's an event horizon, dynamics will not occur?
Yeah, there is, and there is a sense of, you'll see that in a minute. Yeah. There is this, yeah.
So is that was an inertial observer?
Well, no, Allison, in order to make an optimal experiment, she's got to be in a rocket ship because otherwise her components will be radiating. Like
Well,
mad.
no, I disagree with that, right? I mean, if you're an inertial observer, then you're not.
No, you won't be following the killing field and you'll be radiating out to infinity. A particle falling into a black hole radiates out to infinity. A particle that's stationary outside a black hole doesn't radiate at all. It doesn't radiate into the interior if it's just if Alice kept her particle forever stationary. She's not, she's going to separate and recombine, but if she kept it stationary, we'll see this explicitly. If you hold a massive body or a charged particle right outside a black hole, accelerating, it doesn't radiate to infinity or into the black hole. But if it's falling in, it does. That's just this, it comes from the killing field. Yeah.
What is the mathematical formalism that you're using? Because you
Yeah.
we use quantum field theory in curve space.
That's what I'll be doing, yeah.
But quantum mechanics and general relativity.
Yeah, no. Everything is in the framework of, so all these states will be computed. Well, this is in QED, by the way. So this is QED in curved spacetime. But what we'll be considering is Alice has a charge superposition and she's separating the superposition. We neglect the fact that the current itself the current itself we consider to be essentially like, well, to do the calculation will be a classical type source. But it'll be in different branches of the superposition, whether or not it had gone left or right. So like, we're gonna not consider the fact that the current is gonna, has a little bit of fluctuate. You can account for that. That's not gonna be a big deal. The more important thing is whether or not Alice makes a macroscopic superposition of Coulomb fields in the exterior. So that's why I do the electromagnetic case first, because it's really simple and there's no question about it. In the gravitational case, we'll be firmly in the context of linearized gravity, where each of these are test masses creating small gravitational fields in the exterior. You have a question? You have a question? How many questions am I supposed to take? Yeah.
So you're saying that basically Alice is stationary and just like following like a more like on
Yeah, that's her lab. Yeah, that's right.
So, is she stationary at the horizon?
What?
Is she stationary at the horizon or
No, it's
nothing particular to the horizon? Or is she like far away?
no, she's far away. I mean, she doesn't need she's any distance away at the moment. Any proper distance away from the black hole, and her lab is stationary. If it wasn't stationary, I claim I can. We'll see the exact solution in a second, but we'll see exactly what I'm saying. But it's worthwhile to go through the exercise to see that if you have a body falling into a black hole, it will radiate to infinity and into the black hole. In order to make sure the body doesn't radiate, you have to hold it stationary. And so this is, I claim, the optimal experiment. Any other questions? Okay, so this is Alice in the exterior. This is, if you're not familiar with Penrose diagrams, this maybe is a little bit easier to see. This is the black hole. The V along the horizon is the affine time along the horizon. That's related to the more conventional time in Alice's lab, which is this killing time in Alice's lab by an exponential. R here is the proper distance off the horizon of the black hole, given here. And well, actually it's a radial null distance, I guess, in this case, because you're propagating off the horizon. And then the cross sections of the black hole are two spheres. So that's what's given here. Capital indices in the talk will refer to things on the sphere. Okay. Okay, advance the slide. Yeah, here we go. Okay, so now we're gonna, well, a few of you had some questions about what a body looks like in the exterior of a black hole. That's the whole point of this slide. So let's consider now the warm-up problem of what is the radiation produced by a charged body that's initially at some distance from a black hole, and I'm just gonna move it to a new distance here, which is displaced by an amount little d. Okay. And so this is the picture, this is what I'm doing, and I want to know how much radiation is produced on the horizon of the black hole, no matter, and I want to consider the case where I'm doing this motion arbitrarily slowly. Okay. So that sounds like a complicated problem, and indeed it is if you wanted to know the radiation everywhere, but we only want to know the radiation on the horizon. And Maxwell's equations on the horizon of the black hole takes a very simple form, where it relates the radial component of the electric field generated by the charged body. So that's the Coulomb field that is non-zero due to the fact that Alice has created the superposition and will respond, with retardation effects if Alice moves in the exterior of the black hole. That's what this radial component of the electric field is. That's the Coulombic field of Alice's charge. And the left-hand side here is related to the so-called horizon radiation. So why is that the horizon radiation? Well, okay, this is a laser pointer. So if the radiation is propagating radially, and that's the black hole, that means it's oscillating transversely, which in this case is angularly. Okay, so this is the divergence on the sphere of the horizon radiation is equal to the time variation of any Coulomb fields that Alice moves in the exterior. Okay, does this equation make sense? Okay, so now if I have a static body, as I was just saying before, then that's the situation in which you can just check the horizon radiation particularly vanishes. And in particular, the Coulomb field registered on the horizon is constant. Okay, and just given in magnitude by the charge over the proper distance from the horizon squared. Okay. Now what she's going to do is she's going to take this charged body and move it to a new location. So this ER is not going to remain constant anymore. It's going to change by Alice moving things in the exterior of the black hole. And in this process, I'm moving it arbitrarily slowly. The radiation will be arbitrarily small, okay, due to the displacement in the exterior of the black hole. However, there is one thing to point out, which is that she's moving it from one location to the other, and it registers on the horizon that she's moved it from one location to the other. So the change in the Coulomb field on the horizon is not zero. If I integrate this equation, what that says is, no matter how small EA is, the radiation is, the total integral of this radiation is not zero. This should be no cause for alarm right now. It's just useful to note that the total integral of this radiation is, yeah. No, it's a divergence on the sphere, right? So the capital indices refer to things on the sphere. The radiation is propagating, oscillating transversely, which is in these coordinates in the spherical directions. And so it's this divergence on the sphere. That's not so important. All you should think about in this equation is that time variations of Coulomb fields in the exterior of the black hole generate radiation. That's all. Okay, and one other thing to point is that if the electric field is the time derivative of the vector potential, which means that this implies that the vector potential, this integral is not zero, which means that the vector potential must suffer a permanent change on the horizon due to the displacement of this charge, okay, in the exterior. That's all I'm saying, where the size of this change in the vector potential, so vector potentials are not gauge invariant, differences in vector potential are gauge invariant, and the change in this vector potential is roughly proportional to the change in the Coulomb field that Alice generates in the exterior. Okay. For those of you who are familiar with the memory effect and the black hole memory effect, this is exactly analogous to that effect. I think soft photons or something, or gravitons were mentioned earlier. That's exactly what's going on here. And now what we need to compute is what are the number of entangling photons produced in this process. Okay. So to know that, well, if you want to know the number of photons, you have to first choose a vacuum. What is the zero photon state, or where am I setting my zero relative to? So the vacuum in the exterior of the black hole is this so-called Unruh vacuum. That's the vacuum produced from a black hole formed from gravitational collapse, which at low frequencies is actually, on the horizon, is equivalent to the so-called Hartle-Hawking vacuum. If that is not important, or if that is not familiar or obvious to any of you, it's not important. The basic point is that the number of photons, expected number of photons emitted in this process, there's a formula for it in terms of the vector potential I gave you before. Okay, which is that if you take this vector potential, you Fourier transform it with respect to affine time, you square it and multiply by frequency, and you integrate over positive frequencies and angles, that's the number of photons that Alice has produced in this process. We're trying to keep this number small, right? Otherwise she decoheres. Okay, but we can't keep it small. Well, we definitely can't keep it small if she displaces it and leaves it there forever. Because if she displaces it and leaves it there forever, which is not what we're going to do, because we want to do an experiment, we want to bring it back later. But if she leaves it there forever, then the Fourier transform of this waveform is the Fourier transform of a step function, which diverges like 1 over frequency. And the number of photons, therefore, is logarithmically divergent in frequency. What does that mean? If Alice does the totally unphysical thing, which is not going to, she can't do this, which is take a charge and displace it outside a black hole and leave it there forever, then she radiates an infinite number of soft horizon photons, and she's totally decoherent. Okay. Obviously, that's not what she's going to do. She's going to displace it back after an amount of time to do an interference experiment. After a finite time, capital T, the number of photons is finite, but as similar arguments, it's going to be large for large t. Okay, 5 minutes? Okay, so yeah, okay, so this number of photons is logarithmically divergent in the affine time that Alice has displaced the charge. But therefore, well, note that the affine time was related to the proper time in Alice's lab by this exponential factor. So in the time in Alice's lab, the number of photons will linearly grow in time that she's displaced it. And the prefactor is there because now I can tell you how black holes decohere, like how quickly. Okay, so this number of entangling photons of the black hole is also, well, the number of entangling photons will also grow linearly in time, and Alice will be decoherent after she emits an order 1 number of these entangling photons. So the time of decoherence, well, these estimates are both meant to explain that, Sugata, you don't need to worry about this effect if you're trying to, well, if your experiment was charged, you don't need to worry about this effect. If your experiment was a massive superposition, you'll see you also don't need to worry about this effect for black holes that are distantly far away. The effect strongly depends on distance, which makes sense. Bob inside the black hole should have a very hard time measuring this sensitive superposition experiment. Yeah, go ahead. So in particular, if the sun was a black hole and we were doing this experiment on the Earth and separating electron over a meter, then Alice would be decoherent, but it takes an inordinately long amount of time. However, if Alice is closer by, about the ISCO 6m from the black hole, then the decoherence time is 5 minutes. Bob can do quickly or relatively quickly. I mean, maintaining a superposition for 5 minutes is already quite difficult. So, and there's astrophysical effects and so on and so forth. But in a perfect world, it's Alice can't, this is the fundamental bound. The Earth-based proposals, the one that's, that people are trying to do, also don't need to worry. You can get decoherence times that are short, but you got to do crazy things. And I think in the paper, we put a mass, the mass was the Earth, separated over its own radius, and the sun was a black hole. And again, this distance to the 10th really kills you. So you really need these really, really big masses and really big superpositions, and then you'll get human numbers. However, if you were 50 kilometers away and you had a mass of 1 kilogram superposed over a meter for a black hole being a sun, for the sun being a solar mass black hole, then the decoherence time is human scale, at least. But still, don't worry about the effect in that regard. Okay, so how much time do I have? Yeah? Not so strict? Okay, so I have two things to explain to you that I'll let the audience decide. So you can now, well, there's two things you can do. You can understand the extreme versions of this, what happens in the case of an extremal black hole. That is an interesting case that that kind of pushes up or explains or gives credence to this idea that bobs are inside the black hole and so forth. And then there's the other one, which is how does this effect compare to other bodies like this cup of coffee, which will also decohere a quantum superposition. I think maybe I'll do the second one because yeah, and I'll feel free to ask me about the other one. This is the extremal black hole case. Okay, so as I mentioned in the beginning of this talk, it's black holes. Well, I hope I convince you. Black holes decohere quantum superpositions and place fundamental bounds on their coherence, but they're not alone in this regard. It's interesting that they do it, but any physical body will decohere a quantum superposition. So, you know, I have a cup of coffee here. This is a glass of water. If Alice accidentally left a glass of water in her lab and she had her superposition around and she made her superposition in her lab, well, then the glass of water will go into a quantum, well, the degrees of freedom in the water molecules and so forth will get sloshed around based on whether or not the superposition had maintained stationary or been displaced to the right closer to the glass of water. And thereby the quantum state will go into a superposition of the undisturbed water and totally disturbed water. And if it has some viscosity and some dissipation, this will be decohered relatively quickly just by the presence of the glass of water in the lab. Okay, so everything I said was very tied to horizons. I think it gets kind of to the point that I said before, but that's horizons. Well, in order to compare the effect, you need to reformulate this in terms of degrees of freedom entirely present in Alice's lab. Okay, so which is what we did here. And it's not important you understand this formula. So you can rewrite the number of photons, this thing that I was telling you about that tells you how much Alice is decohered. Remember, when this is order 1, Alice is decohered. You can rewrite it in terms of a local 2-point function in Alice's lab. These are the local vacuum fluctuations in Alice's lab, where you're taking the vector potential, the 2-point function of the vector potential in Alice's lab, and smearing it in, integrating it in with the difference of the charge currents of whether or not Alice went on path 1 or path 2. If you didn't follow that, that's okay. It's just the point is that the local vacuum fluctuations in Alice's lab, you can show are, well, in some sense, responsible in this way for her decoherence. And in particular, what you'll see is that, well, you can rewrite it in a much more suggestive way, which is that you can write it as the charge times the distance times this time here. So these are factors that appeared previously when we calculated the number of photons. But as opposed to a horizon integral calculation, as before, what's presented here is the fluctuations of the radial component of the electric field in Alice's lab. Okay, so this is the fluctuations of the dipole, the power spectrum of the dipole fluctuations in Alice's lab over, well, and then over d cubed, that's the fluctuations of the electromagnetic field in Alice's lab at 0 frequency. Okay, so this is an equivalent formula for the one I presented before. So about a year ago, I derived this formula, and then I threw it away because this is a bit crazy. Black holes don't have multipole moments. They only have, you know, the ADM mass. They don't have dipole moments or quadrupole moments or so forth. But that's not true quantum mechanically. So quantum mechanically, a black hole emits all the way down to 0 frequency. That Hawking radiation, the radiation that gets out to infinity, is not the low frequency radiation never makes it out to infinity. It gets bounced back into the black hole. But these low frequency Hawking quanta do give rise to measurable effects at finite distance from the black hole. And in particular, what you can show is that this is not 0. So let me show you again. So this is again a conformal diagram. It's not to scale. The wavelengths are very, very, very long wavelengths. Hawking quanta. These Hawking, I didn't show the collapse, but these Hawking quanta, these very low frequency Hawking quanta are produced by the collapse of the body. The collapse of the body produces these very, very low frequency Hawking quanta. In the absence of Alice, they would just reflect off the angular momentum barrier and go back into the black hole. Okay. So there would be no radiation emit, you don't see this as Hawking radiation. However, at a finite, now if you set up a finite distance experiment from the black hole, as the one I've shown here, you will be sensitive to these low frequency quanta. These low frequency quanta have a long tail. They have a tail that goes like 1 over r to L, L being the some, in this case, L being 1 for the dipole part. Okay. And in particular, the Unruh vacuum has a large population of these very, very low frequency Hawking quanta. The density of states diverges as you get down to 0 frequency. And therefore, what you can show is that the black hole, what's happening is that the black hole, because from the collapse, it produces all of these very, very low frequency quanta. This low frequency quanta sets up 0 frequency or very low frequency dipole fluctuations present in Alice's lab. I put in the numbers just to show you it's, human scale dipole fluctuations and quadrupole fluctuations in Alice's lab. Those quadrupole fluctuations are what stimulate the emission of these very, very low frequency quanta, causing the decoherence of Alice's particle. Such quanta are not present if you had a thermal state in Minkowski spacetime. You do not get this divergent density of very, very low frequency modes. These quanta are not present in the spacetime of a static star if you just had a star around and you didn't, it's very important that you form this black hole from collapse. Okay, so how do you compare to this cup of coffee? Well, any material body will mimic the exact same effects as a black hole if you can get the dipole and quadrupole fluctuations outside the body at low frequencies to be matched by the black hole of the same, well, if you want to do an apples to apples comparison, of the same size and temperature. This can be, so this was recently investigated by Biggs and Maldacena, and this can be done in the electromagnetic case. Essentially, in order to get dipole fluctuations at very, very low frequency, you need a high resistivity material. And, but you can achieve these in laboratory experiments. In the gravitational case, this needs, if you have a fluid, viscosities that are enormously bigger than anything one can fabricate or is humanly achievable. And it's really just coming from the fact that a black hole seems to be extremely efficient in its quadrupole fluctuations, in the sense that it's not a lot of material. If you try to replace a body by the same size as a black hole, a body would have much less density than a black hole, and therefore have much harder time generating quadrupole fluctuations to decohere Alice in a similar way. So the gravitational case appears to require extraordinary properties of matter. Okay, so I think I better end. Yeah, so I won't say everything I've said is basically I've already stated in questions or comments. So what I'll end with, I think, is that, well, I think the fact that horizons decohere quantum superpositions as if one was interacting with degrees of freedom present behind the horizon, that's actually was more fleshed out in a recent paper with Bob and Jonah. Behind the horizon may be of fundamental significance to our understanding of the nature of such structures in the fundamental theory, in the spirit that Feynman had in mind. And I'll just end there. Go ahead.
For the nice talk. Question on like an operational understanding of Alice. What
Yeah.
Has like a trap with a particle.
Yes.
That are going on a time like
Yes.
following stationary outside the black hole, and
Yes.
then she creates a superposition.
Yes.
And then one particle gets closer to the horizon, and the other.
That's right. Well, it doesn't really need to be closer. You could be angularly. You just need a difference of gravitational fields. Those difference of gravitational field doesn't matter what direction they go. For simplicity, just considered radial, just to make the calculation simpler, but and radial is optimal for the black hole. It's much difficult for the black hole to measure angularly separated masses.
Because
Yeah.
in our community, when we try to do these calculations on like predict superposition, and then you need to recombine it.
Yeah, yeah.
This is called, Humpy-Dumpy effect, and like when
Yeah. Well,
combine.
yeah.
When you get closer to the horizon, it can in some sense be seen as like a frequency shift, because like your droplet gets, I think, wider due to the.
Yeah, so all blackening factors and frequency stuff, you can Alice can be far away, you know, like at 6M, where the space-time locally in her lab is essentially, you know, the curvature scales are very small and it's flat space-time. So like any of those kind of effects are very subleading to would be subleading to this. Yeah. So like, you know, like for.
Be seen as like
Yeah.
a different like operation that she should
Yeah.
have performed in order.
Yeah, so like you know, for example, like there's going to be, you know, because this is experiencing a slightly different gravitational field than this one, there'll be relative phases produced between branch 1 and branch 2, for
But
example.
also different
Yeah.
acceleration.
Yes, well, those are related to each other, right? Like the point is that there'll be relative phases here, but Alice can locally in her lab, you know, account for that phase difference. The radiation emitted that she has lost is lost it's out of her lab. So we're allowing Alice to do anything she wants in her lab to account for any loss of, you know, local coherence by, you know, the fact that path 1 is slightly different from path 2 and so forth. Yeah.
The black hole is completely deterministic, so
Yeah.
she can calibrate.
But she has to do 2 operations differently.
Yeah, no, she will, but you can do like, you know, those are practical considerations that she needs to take into account, is that there'll be a relative phase shift from the fact that this is experiencing, you know, this is accelerating a little bit differently than this one, and she's going to have to take that into account. But she's she got a lot of funding and she's a really good experimentalist. Yeah, go ahead. Oh, sorry, you had a question.
So if you can have your experiment at any finite distance from one event horizon,
Yes.
then your superposition is in the direct midpoint between 2 event horizons.
Yeah. I think they would just add. I don't think I mean, we're firmly within the context when you do the calculation in perturbative quantum gravity, where these are just sourcing essentially linear fields, where the back reactions of the fields are negligible because the energy of these fields are arbitrarily small. So in that case, the theory, I think the linearity of the theory would then, I think, imply that you just get an additional contribution from each, you know, horizon or so forth. But don't quote me on that. I know I'm being recorded, but yeah, I may revisit that point, but I don't. I would think it just adds, at least to a very good approximation.
Okay, so the way I understand this, correctly if I'm wrong, if Alice is relatively far from the black hole, then the main effect that causes the decoherence is this difference in like the gravitational field that are apparatus fields. And when she gets close to the horizon, the main decoherence effect would be the AMS property of the field, that it becomes thermal at the horizon.
Well, yeah, I mean, so there's Hawking radiation. I mean, can I try to answer your question by explaining 2 points, and then you can tell me whether or not I've answered your question? Okay, so there's Hawking radiation. So you can ask, there's Hawking radiation. There's radiation that goes out to infinity. That's roughly a frequency, you know, determined by m. You know, and that radiation, you can wonder whether or not there's like collisional decoherence. So what this decoherence that I'm talking about here is by the kind of coherent fluctuations of these very, very low frequency modes, right? But there's also just going to be collisional decoherence, you know, just literally a high frequency or order, you know, photon frequency 1/m, just literally hitting Alice's superposition, as if, you know, similar to if she was just sitting in a, you know, radiation bath and it just was colliding with her particle. That can be made arbitrarily small because the separation, we're assuming that Alice does not create the superposition of order m, right? If m is a kilometer-sized black hole, we don't want we're not considering Alice to making a superposition of size m. So a thermal bath, if you're, if the wavelength, if you're not on the order of the wavelength, if you're much smaller than the wavelength of the thermal photons, you can suppress the decoherence due to just collisional Compton scattering. However, you can't suppress this effect. This effect is the very low frequency fluctuations of the field, and that's only present in the case of the black hole. Did I even answer your question? Or I'm delineating two different kinds of decoherence due to radiation. One is kind of radiation you would get even in Minkowski spacetime in a thermal bath, and then the other one is radiation in this case.
Okay.
Yeah.
Okay, I guess we can go for coffee and more questions.